Siete sempre in 3, questa cosa...
Scusi, io la sento, per sbaglio, anziché rispondere, ho chiuso la chiamata.
Va bene, non ti preoccupare. Allora, stiamo registrando adesso, ora faccio lo sharing. Avete per caso provato a sentire i vostri colleghi che fine hanno fatto?
No, mi dispiace, ma mi sono dimenticato di parlarne al riguardo, quindi non so
Beh,
dirle.
se avete una chat, mi pare che avete voi un WhatsApp, un gruppo WhatsApp o qualcosa.
Sì, ce l'abbiamo, mi sono dimenticato.
Ok, vabbè, provate a nel senso, potrei mandare anch'io la mail, però insomma, se, mi sembra più elegante che lo facciate tra di voi. No, la questione è questa, io, come sapete, avete la lezione registrata, vi metto anche le scansioni di tutto quello che scrivo, quindi ovviamente online trovate tutto, però questo non deve essere una ragione per non seguire la lezione, cioè è semmai un aiuto in più che vi do io, però è chiaro che non mi sto riferendo a voi tre, ma a tutti gli altri. Va bene, dai. Allora, schermo intero. Beh. Non me lo fa condividere. Ah, devo cliccarci sopra prima, è diverso qui. Ok. Va bene, adesso dovreste vedere il mio schermo. Oh, benissimo. Allora, iniziamo adesso il modulo 7. Questo diciamo, è un modulo che ci porterà sostanzialmente tutta la settimana, comunque diciamo oggi, domani e metà della lezione di venerdì, in cui adesso parleremo in dettaglio di come si studia la struttura interna del protone e come anche diciamo, la si parametrizza in termini delle proprietà dei suoi costituenti interni, quindi quark e gluoni. E chiaramente un capitolo legato al capitolo che abbiamo appena finito, cioè al capitolo della QCD, perché chiaramente l'interpretazione della struttura interna del protone non può che essere chiaramente basata sulla QCD. Però ci arriveremo a poco per gradi, proprio diciamo, dal punto di vista sperimentale, quindi man mano diciamo, che si è aumentata l'energia, come è aumentata anche la risoluzione, okay, per quanto riguarda la comprensione della struttura del protone, come si è arrivato poi a una comprensione moderna e attuale diciamo, della situazione. Ok, so electron-proton scattering provides a powerful tool for probing the internal structure of the proton. And in fact, electrons are ideal probes for studying the nucleon structure for at least two reasons. First of all, they do not feel the strong force. Clearly, electrons do not carry color charge. So they can provide precise information about the distribution of the electric charge inside the proton. And the second reason is a practical one, is that ultra-relativistic electron beams are relatively easy and cheap to obtain at accelerators facilities. Okay, the mass of the electron is just half an MeV, so to get ultra-relativistic electrons, you just need a few MeV of energy. Now, in the past and also in the present, muons and also neutrino beams have been extensively used to study the proton structure. In particular, neutrino proton beam, proton scattering that we will not study in this course, is clearly regulated by the weak interaction. Okay, not the electromagnetic, but the weak interaction, of course. So, at low energies, the dominant process is elastic scattering. So electron-proton that goes into electron-proton, and the proton remains intact. So in this case, the incident electron interacts electromagnetically with the proton, the entire proton, okay? And the process can therefore only reveal global properties of the proton, such as its charge radius, as we will see later on, okay? However, if we now go to higher energies, okay, now the dominant process is the so-called deep inelastic scattering, or DIS, where the high energy electron interact with a target proton. The scattered electron is detected in the final state, and then X denotes here all the final state hadronic particles that are not in general detected in this process. Okay, so in this kind of process, the proton explodes, okay, it breaks up because the energy of the electron is really high. so all the constituents of the proton, which are quarks and gluons, essentially hadronize into some hadronic final state, which is not detected. And typically, people only detect the scattered electron in this kind of inclusive measurements. Okay. Now, the underlying process is the elastic scattering of the incident electrons from the point-like constituents of the proton, the quarks, as we will see. This we will study in detail tomorrow. Okay. And DIS, so deep analysis scattering, provides information about the momentum distribution of the quarks inside the proton. So essentially, at low energy, the dominant process is elastic scattering, okay, which is a low energy process, so it only reveals you global properties of the proton, because the spatial resolution is very limited. If you increase energy, you enter into a regime of deep analysis scattering. Your electron is very highly energetic. The spatial resolution is very, very high, and you can really probe the dynamical structure of the proton in terms of quarks and gluons. Okay. Now, the spatial resolution of the incident electron depends clearly on their momenta, and ultimately on the wavelength of the exchanged virtual photon. And depends, of course, on how large is the wavelength of the photon compared to the radius of your target proton. And so we can identify 4 different regimes. The first regime is where the wavelength of the photon is much, much larger than the radius of the proton. And so electrons are non-relativistic, and the process can be described in terms of elastic scattering of the electron in the static potential of an effectively point-like proton. So the energy is so low and the wavelength is so large, okay, that the electron see the proton essentially as a point-like object that produces a static potential all around. Now, the second case, the second regime, is where now the wavelength of the photon is more or less of the same size of the radius of the proton. And now the electron energy is high enough to reveal the finite size of the proton. So the proton does not look anymore as a point-like object, but it reveals its finite size. Okay, we know that it is of the order of 1 Fermi. And the cross-section calculation needs to account for its extended charge and magnetic moment distributions. Okay, so it is not anymore point-like, but there is some distribution of charge and of magnetic moment. And this is essentially the main subject of the today's lesson. Then we can go even farther in energy, okay? So we enter in a regime where the wavelength of the photon, the virtual photon, is now smaller than the radius of the proton. In this case, the elastic cross-section becomes small, and the dominant process is inelastic scattering, where now the virtual photon probes the internal structure of the proton, still with low resolution, but at least can start to see the 3 valence quark, for instance. Okay, the proton remains intact, but in this case, it can be excited to some nuclear resonances, like the delta resonances, for instance. And then we have the final regime, where now the wavelength of the photon is much, much smaller than the radius of the proton. This is, in fact, the deep inelastic scattering regime. Now the spatial resolution is so high that the virtual photon can resolve the complex dynamical structure of the proton, you see, in terms of quarks, gluons, valence quarks, C quarks, etc. This we will study tomorrow. And clearly the proton in this regime breaks apart, okay? It explodes, and then all the internal constituents will hadronize. So at the end, of course, you will only reveal hadrons in the final state, together with the scattered lepton here. Now, the electron-proton elastic scattering is dominant at low energy, as we have seen, and therefore a non-relativistic treatment is adequate at this level. Okay. In particular, in this very low energy regime, the proton can be considered as a point-like, spinless, charged particle with infinite mass. The question of infinite mass is, if you want, to account for the fact that we can, since the energy of the electron is so low, we can completely neglect the recoil energy of the proton. So essentially, the proton stays at rest in the process, okay? And this, we can say that it is what we expect if the proton would have an infinite mass. And so, under these conditions, it is seen by the incoming electron as a source of a static central potential. Okay, Well, strength depends only on the distance between the electron and the proton. So the proton in this very first low energy regime is a point-like, spinless. So for the moment, we forget about the spin of the proton. Okay, it is charged, of course, and we assume that it has an infinite mass. Now, assuming a Yukawa potential that we studied already several times, if you remember, we derived the transition probability amplitude, okay, in one of the first chapters of this course. That was G0, G divided by Q square plus M square, if you remember, okay? And in the classical view, this transition probability amplitude describes the probability amplitude for the scattering of a particle, an electron in general, specifically, coupled through a constant G0 to a static potential of intensity G. Okay, so this we discussed a long time ago, and it is the classical interpretation of this transition probability amplitude. As you remember, there is also a more modern interpretation, which is the one proposed by Yukawa. And in the Yukawa approach, this transition matrix is interpreted as the boson propagator, if you remember. So the probability amplitude for the exchange of a boson of mass m and momentum q between the two interacting fermions. So essentially the electron here and the proton there in this case. In particular, for the case of electromagnetic electron-proton scattering, one has the following conditions. So the exchanged boson is the photon, so the mass is 0. So this m goes to 0. The constant G0 is nothing else than the electric charge of the incident electron. So G0 is just the charge of the electron, E. And the constant G divided by 4 pi, the one that enters here, okay, in the Yukawa potential, corresponds to the charge of the proton. Okay, so G, if you multiply by 4 pi, is 4 pi times ZE, where for the proton, clearly Z is equal to 1. So G is 4 pi E. Okay, so let's now put all these things together and see what is the shape of the cross-section that we obtain. Allora. Okay, so the transition amplitude in general that we derived was G0 G divided by Q square plus M square. Okay, this we derived in the, if you remember, in the non-relativistic approach. And we are now allowed to use this approach because we are talking about low energy electron-proton scattering, okay? So now, G0, as we said, is just the charge of the electron. M is equal to 0, is the mass of the photon. G is equal to 4 pi ZE, that is 4 pi E, because the proton has Z equals 1. And then you remember we are working in the assuming that the proton has an infinite mass, okay? So let's say the mass of the proton, we suppose it is infinite, and this corresponds to neglect the proton recoil, so that the momentum of the incoming electron is more or less the same as the momentum of the outgoing electron, and so we can just call them both P. Now, let's calculate now the transferred momentum squared, so the Q squared. The Q squared is given by Pi minus Pf all squared. So these are standard 3 momenta, okay? So now we take the square, so this is Pi squared plus Pf squared minus twice Pi dot Pf. Now, as we said, the initial momentum and the final momenta in moduli are the same. So this is essentially twice P squared minus twice P squared cosine theta. This we can collect. So twice P squared, 1 minus cosine theta, and then we apply some standard trigonometric formula, and this gives us 4 P squared sine squared of theta half. Okay. So this is our squared transferred momentum or if you like, the momentum of the exchange, the squared momentum of the exchange with the photon. So now we can substitute all these into our transition matrix. So TFI, which is again J0 G divided Q square plus M square, becomes, in this particular case, let's take here an approximate equal. So we have on the numerator 4 pi E squared, which is the product of the two charges. And in the denominator, the mass is equal to 0, and the squared transfer momentum, as we calculated, is 4 times P squared sine squared to theta half. Okay? So let's call this equation 1. Now we can write down the expression of the cross-section for elastic electron-proton. Okay, so let's say elastic electron-proton scattering at low energy. Okay, so the differential cross-section, the sigma in the omega, elastic, at very low energy essentially corresponds to the total cross-section. Okay, so at the low energy, the total cross-section is essentially elastic. Okay, when you increase the energy, then the elastic component becomes smaller and the inelastic component becomes more important. Okay, but since you are working low energy, this essentially corresponds to the total cross-section. And here we can now write down the formula, the general formula of the cross-section that we derived through the Fermi golden rule, if you remember. Okay, it is 1 divided by 2 pi squared h bar to the 4th. Then we have the squared transition amplitude, and then we have the spin multiplicity, the final momentum squared, the initial state velocity, and the final state velocity. Okay, so this we derived a long time ago, starting from the Feynman golden rule. And let's now substitute what we have here. So this is going to be 1 divided by 2 pi squared h bar to the 4th, and then we have 4 pi e squared 4 times p squared sine square of theta half, which is our transversal momentum. All these go squared in the cross section, and then we can just copy this one, gf times p square f divided by vi times bf. Allora, fin qui ci siete, ragazzi?
Ok. Ricopro un secondo, ci sono l'ultima riga.
Sì. Va bene, dimmi tu quando posso andare avanti.
Volevo chiederle soltanto una cosa. Il termine sopra è GF, non mi ricordo.
Sì, GF ora ci arriviamo, è la molteplicità dello spin. L'abbiamo ricavato ai tempi, ora
Va bene,
nella
grazie.
prossima pagina lo rendo esplicito adesso.
Ok, grazie. Io
allora,
ci sono.
se ci siete tutti, andiamo avanti, cambio pagina.
Mm-hmm.
Ok. Oh, ok, io sono a posto, vabbè, fa niente. Voilà. Okay, so now we consider that we remember that we are neglecting the proton recoil energy. So essentially, since Pi is essentially equal to Pf, then this also holds for the velocities. We are, of course, in a classical non-relativistic approach. So this implies that Vi is approximately equal to Vf, that we can call just V. And so classically, Pf squared divided by Vi times Vf that we have in our cross-section formula, this is essentially, in our approximation, equal to P squared divided by V squared. And classically, this is nothing else than the mass squared. Okay? So clearly, this is a non-relativistic approach. What about now the spin multiplicity factor that we were just discussing? So if you remember, GF accounts for all the possible spin states of the initial particles. The particle is initial state. So in general, this will be twice SE plus 1 times twice S spin of the proton plus 1. Okay, so this will be the general expression for the case of electron-proton scattering. However, we are assuming that for the moment, so this is the very, very first approximation, that we are neglecting completely the spin of the electron and the spin of the proton. Okay, so if this is 0 and this is also 0, then this turns out to be just 1. Okay. Now, as a last thing, we also work in natural units. So in the following, we just put h bar equal to 1. And so we can now write down the cross-section formula after all these changes. So this is the elastic one. So this turns out to be 4 pi e squared divided by 4 p squared sine squared of theta half, all squared. And then we are just left with m squared divided by 2 pi squared. Now, we can simplify the 2 pi inside the parentheses with the 2 pi outside. And so this results in e squared with 2p squared divided by m. So we put now the m squared here in the denominator, times sine square theta half, all squared. Ok, quindi abbiamo semplificato il 2 pi al quadrato e abbiamo messo la massa al quadrato giù al denominatore. Okay, now again we use the non-relativistic relation between energy and momentum. So final energy, if we neglect the proton recoil energy, will be essentially the same as the initial electron energy. And classically, this is p squared divided by 2m. And so the term that we need here to substitute, which is 2p squared divided by m, is nothing else than 4 times the final energy. And so we can now substitute this into the cross-section formula, and we obtain the sigma in the omega elastic as e to the 4 times final energy squared, sine to the 4th power of theta square, which is essentially proportional to the 4th power of the electron charge and the 4th power of the transferred momentum. Qualcuno di voi riconosce questa formula? Mi sa dire il suo nome preciso? Com'è?
L'andamento è quella dello scattering di Rutherford.
Esattamente. Abbiamo ricavato esattamente la sezione d'urto di Rutherford. Okay? È uno scattering elastico, elettromagnetico, in cui tutto avviene classicamente, quindi non c'è bisogno di utilizzare l'approccio relativistico, e in cui si trascura lo spin, per adesso, diciamo, delle due particelle che interagiscono, e si assume che il protone rimane fermo dov'è, cioè che non rincula. Ok?
Vorrei chiedere una cosa velocissima, scusi.
Sì, certo.
Dicendo che la cross-section elastica era approssimabile a quella totale, mi sono perso il passaggio logico di quello che era successo.
Sì, allora il passaggio logico è questo: se sei a bassissime energie, come il caso dello scattering Rutherford, di fatto tutta la sezione d'urto totale è praticamente elastica, non c'è altro.
Okay.
Man mano che tu invece aumenti con l'energia, la sezione d'urto elastica diminuisce e a poco ti aumenta la sezione d'urto inelastica. Quindi quando vai ad energie molto grandi, diciamo, quella elastica sarà praticamente 0 e quella che domina sarà quella inelastica. Però ripeto, a energie molto basse di fatto è tutta quanta elastica.
Ok, va bene, grazie.
Niente. Allora, se ci siete possiamo andare avanti. Quindi qua rinnoviamo. Ok. So we just obtained the Rutherford cross-section for 2 point-like spinless particles of charge E. And let me note that the angular dependence of the Rutherford cross-section, so the famous sin to the 4 theta half, solely originates from the 1 over q squared term of the photon propagator, okay, as we derived at the beginning. Now, adesso mi collego alla domanda che ha fatto adesso uno di voi. The 1 over q to the 4 depends implies very low event rates for electron scattering with large momentum transfer. So if the q square is large, this cross-section is suppressed, okay? And in fact, at large q square, the elastic scattering is strongly suppressed, and inelastic process becomes instead dominant, okay? So this cross-section here dominates only when q is very small. That is low energy scattering, elastic scattering. Now, we just derived the Rutherford cross-section, okay, using first-order perturbation theory. That is our expression for the transition amplitude, T, and by considering a non-relativistic spinless electron in the starting Coulomb potential of a spinless, infinitely massive proton. Okay, so this was our starting point. Let's now remove step by step all these approximations. Okay, so the first approximation, the first step is now to derive the so-called Mott scattering cross-section. Okay, so now we increase a little bit the energy. So the electron is now relativistic, and so we have to account for its spin. So we will now treat the electron as a Dirac fermion. Okay. However, the energy is still low enough to consider the proton as spinless, and essentially again neglecting its recoil energy. Okay, and this regime is intermediate. Is when the energy of the electron is between the mass of the electron and the mass of the proton. So what happened in this case? So now we have to take into account properly the spin of the electron. We have to treat the electron as a spinor, a Dirac spinor, okay? And as we have seen in QED, for relativistic electrons, there are only two helicity configurations that leads to non-zero currents, if you remember, okay? Those where the helicity is positive, here and there, or where both helicities are negative, okay? So these are the only two combinations in terms of the helicity spinors, if you remember, okay, U plus and U minus, okay. Now, inserting the expressions of the initial and the final state electron helicity spinors and treating the proton again as a point-like infinitely massive Dirac fermion, one then obtains this correction to the cross-section. So the Mott cross-section is essentially the Rutherford cross-section, okay, times a correction term here, okay, which goes like beta squared sine square of theta half. Now, since we are now working in a relativistic regime, at least for the electron, beta clearly is close to 1. And so essentially this is 1 minus sine squared, that is a cos square. So the Mott cross-section, where now the electron is relativistic and its spin is fully accounted for, is essentially given by the Rutherford cross-section multiplied by a cos square of theta half. Let's now see what is the physical reason of this cos square here. So the additional cos square theta half has the effect of suppressing backscattering processes, where the electron is scattered by a spinless proton at an angle close to 180 degrees. Why? So consider the following situation. You have your proton, which is fixed here, okay, not recoiling, and without spin. So spin is 0 for the moment for the proton. And we are coming with an incoming electron with momentum P and spin, initial spin Si, okay? And both are aligned here. So they point in the same direction. In case of backscattering, what happened? It happens that the proton, the momentum of the electron is now inverted. It points in the opposite direction compared to the initial state, but the spin remains unaffected. The spin is still there, and we'll see now in a moment why. So if theta is indeed 180 degrees, okay, so a complete backscattering, the momentum becomes opposite, and this is clear also from the picture here. However, if the target proton is spinless, as we are assuming at this point, it cannot compensate the spin flip of the electron, since this would result in a non-conservation of angular momentum. So, as a consequence, the direction of the electron spin must remain unchanged. Ok? In altre parole, siccome stiamo assumendo che il protone non ha spin, ok, in questa approssimazione, un eventuale spin flip dell'elettrone, che porterebbe anche a un'inversione dello spin dell'elettrone, non potrebbe essere compensato da nulla, perché non c'è nessuno spin del protone, e quindi si violerebbe la conservazione del momento angolare nel processo. Siccome il momento angolare si conserva sempre e comunque, in caso di backscattering, il momento cambia direzione, ma lo spin rimane com'è. Il che vuol dire che inizialmente abbiamo una elicità positiva, perché momento e spin sono allineati, nello stato finale avremo una elicità negativa, perché l'impulso punta di qua, lo spin continua a puntare dall'altra parte. Okay? So helicity would not be conserved in case of backscattering, because it is positive in the initial state and negative in the final state. And therefore, the process cannot occur for relativistic electron as a consequence of helicity conservation in electromagnetic processes. And this is ensured by the cos-square terms. Okay, the cos-square term kills completely the backscattering. You put 180 here, you get a 0. So this kills the cross-section for backscattering. Okay, and this is now the sense of the Mott cross-section. Now let's further increase the energy. Okay, so if we now sufficiently increase the energy of the scattering process, we can no longer ignore the proton recoil energy. Okay, and so we have to abandon the hypothesis of infinite mass, the approximation of infinite mass of the proton. And as a consequence, the final energy of the electron will be different now than the initial energy of the electron. So we have to account this, and so considering now a proton of finite mass, MP, so Fm stands for finite mass, one then obtains this relation between the final energy of the electron and the initial energy of the electron in terms of the scattering angle and the mass of the proton, which is now finite, okay? And so now the Mott cross-section for finite mass proton is given by the Mott cross-section, the one I just showed you before, times this correction factor here. Okay, the ratio between the final and the initial energy of the electron. And from this kinematic relation, you can just write down explicit in this way. Okay, so this is now a more precise description of the cross-section when the energy of the electron is such that we cannot neglect anymore the proton recoil energy. Clearly, if you put again infinite mass here, this terms goes to 0, all this goes to 1, and we are back to the standard Mott cross-section. Okay. Now, let me point out that now at this higher energy, the relativistic approach is mandatory, okay? So it is no longer possible to describe the scattering in terms of the 3 momentum transfer. Instead, we have to work now with the Lorentz invariant squared 4 momentum transfer, okay? So let me make this more explicit.
A question.
Sì.
Are you meaning also in this case or in the following one?
Che cosa?
That we have to use the Lorentz invariant for momentum instead of the 3 momentum.
Okay, yes, it is essentially from this point on, because we are now in a process of increasing step by step the energy of the process, and so removing one by one the approximation that we did at the beginning. Okay. However, in between of this lesson, when we will speak about form factor, we will at a certain point come back to the non-relativistic treatment. Okay. By the way, the logic is to increase the energy, remove the approximation one by one, and so from this point on, use the relativistic approach. Ok? Allora, adesso andiamo qui. So, pagina 3. So this is now the square of the 4 momentum, which is a Lorentz invariant. That is now the initial 4 momentum minus the final 4 momentum squared. And this is energy squared minus 3 momentum squared. So we can now develop this. So this is initial energy squared plus final energy squared minus twice EI EF minus initial 4 momentum squared minus final 4 momentum squared plus twice PI PF. Sorry, this is 3 momentum, not 4 momentum, but 3 momentum, of course. And here we have the scalar product. Now we collect as usual. So EI squared, initial energy squared minus initial momentum squared plus final energy squared minus final momentum squared. And then we are left with minus twice initial and final energy plus twice pi pf cosine of theta. Now we realize that this is nothing else than the mass of the electron squared, and also this is the mass of the electron squared. One is the incoming electron, the other is the outgoing electron, but the mass clearly is the same. And so this is essentially twice the mass of the electron squared minus twice initial energy, final energy minus pi pf cos theta. Now we can clearly neglect the mass of the electron because we are talking about relativistic energies. So we can completely neglect this term here. And also we can approximate the energy with the momentum for the electron because we are neglecting the mass. And so this is approximately equal to minus twice EI EF 1 minus cos theta. And finally, we apply again the trigonometric formula. So we get 4 minus 4 times initial energy, final energy, sine squared of theta half. Now we realize that this object here is by construction negative. Okay, so we have a squared q square, which is at the end negative. Okay, so in order to work with the positive quantities, we define now the capital Q square, which is just as minus small q square, and so this is 4 times EI IF sine square of theta square. So the capital Q square is, let's say, the negative squared transferred force momentum of the process, which is now positively defined. Ok?
Ok.
Allora, torniamo adesso di là. Now, let's continue in our process of removing one by one the original approximations. So the next level is now to include the spin of the proton that we neglected so far, okay? And so we can now regard the proton as a point-like Dirac fermion. In doing so, we have to include now an additional term in the potential, which accounts for the interaction between the magnetic moments of the proton and the electron, because now they are both with the non-vanishing spin. And so the spin-spin interaction has to be taken into account. We will not derive the details here, but let me just tell you that this results in an additional correction term, which is proportional to the sine square of theta half in the cross-section. So back to our story. The sigma in the omega Dirac, where we mean that we are now considering the proton as a Dirac particle, so a point-like, but with the spin 1/2, will be given by the Rutherford times the correction for accounting for the not negligible recoil energy of the proton, times the cos square coming from the Mott cross-section, so to suppress the backscattering, times we have this now additional term here, okay, which arises from the magnetic moments interaction between the proton and the electron, or if you like, the spin-spin interaction term, okay? Now, we can put the cosine outside of this parenthesis, okay? And so we obtain outside the Mott cross-section for the finite mass proton, and what we are left inside is 1. Now we have to divide the sine square with the cos square, so we get here a tangent square of theta half, okay? So this is now the new differential cross-section in the case where we consider both the electron and the proton as Dirac particles with spin. But this is not the end of the story, because if you remember, and you know very well now, the magnetic moments of the protons and also of neutrons is not the Dirac magnetic moment, okay? We know that we have now an anomalous magnetic moment, okay? Because we cannot regard, in fact, the proton as a Dirac particle, because the proton is not an elementary particle. It has its own internal structure. And we have seen already in the framework of the quark model so on the SU3 flavor symmetry, that we can actually construct the anomalous magnetic moment of the proton in terms of that of the constituent quarks, if you remember. Okay, so we know, for instance, that for the proton, the magnetic moment is 2.793 times the nuclear magneton. Okay, and for the neutron is minus 1.913 in terms of in units of the nuclear magneton. And this we can parameterize in terms of these Kp and Kn, which essentially account for only the anomalous part of the magnetic moment. Okay, so if those would be 0, then the neutron and the proton will behave just exactly as a Dirac particle. Okay, with just 1 in units of the nuclear magneton. Okay, as it is for any Dirac particle. Whereas we concentrate on this Kp and Kn, all the anomalous part of the magnetic moment of the proton and the neutron. So we have to take these into account also in the cross-section formula. And so now this cross-section formula has to be transformed a little bit to account for this. So now we call it the Dirac with anomalous magnetic moment. Okay, so we removed this additional approximation, and it is given by the mode cross-section for a finite mass proton, and now also including this anomalous magnetic moment of the proton, or if you like, also of the neutron. Okay, so we still have this structure, okay, a constant plus the tangent square, but now we have also these objects inside. Now, let's attack now one of the last, actually the last approximation, that is the one that the proton has been considered as a point-like object so far. Okay. Now, to account for its finite size, which is of the order of 1 Fermi, so clearly not a point-like particle, and in particular for the fact that its electric charge and its magnetic moment are not point-like, but they come with some special distribution, rho, okay, we need to introduce the form factors. Okay, and this, let's do it properly on the board. Domanda vi faccio: nel corso dell'anno scorso di Lenisa avete studiato i fattori di forma del nucleo atomico?
Allora, adesso nel dettaglio non me le ricordo, però sì, mi sembra di sì, tutta questa trattazione l'avevamo fatta e i fattori di forma del nucleo l'avevamo accennati. Ovviamente
Okay.
non vedendoli nel dettaglio, però sì, non sono cose
Okay,
nuovissime per
va
me.
bene, ok, perfetto. Beh, quindi diciamo, questo mi facilita un po' il compito. Adesso chiaramente non parleremo di fattori di forma del nucleo, ma fattori di forma del nucleone, quindi del protone e del neutrone. Però diciamo il concetto è lo stesso. Ok, allora andiamo a pagina 4. Allora, qui faremo adesso nuovamente una trattazione classica per arrivare, diciamo, al concetto finale, poi diciamo, quello lo svilupperemo anche poi dal punto di vista sperimentale. So let's consider the Coulomb potential generated by a spherical charge distribution at a generic distance r from the center. So, quindi facciamo un sistema di riferimento. Immaginiamo di avere una distribuzione di carica elettrica sferica. Fate finta che è una sfera. Quindi qua abbiamo 0, l'origine, e vogliamo calcolarci noi il potenziale a un certo punto P che dista R dal centro di questa distribuzione di carica sferica. Okay? Nel far questo prendiamo un punto P' dentro la sfera che sarà individuato da un vettore posizione R'. Okay? E quindi possiamo anche definire questa distanza qui come R meno R'. Okay? Okay, so we know from classical electrodynamics that the potential at the Coulomb potential at a certain distance r originating from a charge distribution is given by the charge distribution itself, so r prime divided by 4 pi, then the relative distance, and then integrating over the volume of this sphere, charged sphere. Okay, and in particular we can parameterize our charge density rho r prime as the total charge times the spatial distribution, which is just a function of the space. a function of the coordinate r prime inside the volume of the charge. Ok?
Quindi adesso noi stiamo guardando il potenziale nel punto P della sfera che va dal centro fino a R'?
No, R' è un punto generico dentro la sfera avrà un raggio R, quello che vuoi, chiamiamolo R grande, va bene? Adesso stiamo considerando prendiamo il punto generico P' dentro la sfera e integriamo su tutto quanto il volume della sfera. E ci calcoliamo in questo modo il potenziale a una distanza R, quindi a un punto P all'esterno. Okay? È un problemino da fisica 2 questo qui. Of course, we want to ensure that when we integrate the charge density over the entire volume, we want these to exactly correspond to the total charge Q. Okay, and this corresponds to say that the position distribution, so the spatial distribution, must be properly normalized. Must be normalized properly in order to get that the integral of the charge distribution is exactly the charge, the electric charge. Okay, so let's see how this normalization is done. So f r prime in the cube r prime, we now work in spherical polar coordinates. So this is integral 0 to pi, integral minus 1, 1, integral 0 to infinity of f r prime, and then we have in the phi the cos theta r prime square the r prime. Okay, so this is the volume integral now in polar coordinates. Since now our spatial distribution depends only on r prime, but not on the angles theta and phi, the first two integrals are trivially 4 pi, okay, provides just a 4 pi, the full solid angle, essentially. And then we are just left with the spatial integral. So f r prime squared in the r prime. And this we want to be exactly 1. So this we impose, okay, in order to obtain that the integral of the volume of the charge density is exactly Q. Okay. So we can now calculate the matrix element for the elastic Coulomb scattering from such a spherical charge distribution. And we now use, of course, the simplest description based on the plane wave approximation. Okay. So our matrix element, which is final state, potential, initial state, we can write in a plane wave approximation as, so in Born approximation as minus I PFR. Here we are back to a non-relativistic treatment, okay? Minus I PI scalar R in the volume. Now we introduced
uno dei due esponenziali con segno positivo.
Certamente, è il secondo. Grazie.
Nulla.
Ok, adesso inseriamo qua dentro il potenziale, diciamo, l'equazione 1. Ok? So, this turns out to be, now we have a double integral. And we also introduce, let me put it here, the transfer three momenta Q as Pi minus Pf2. Okay, so we now to introduce 1 and 2 into this expression. So this is E to the IQ scalar R. Then we have rho R prime divided by 4 pi R minus R prime in the cube R prime, which is the integral over the charged sphere, and in the cube R, which is the integral over all the total volume. Okay. Now we make a trick. We multiply and we divide by one of these exponential. So this is equal to E to I Q scalar R minus R prime times E to I Q R prime. Quindi qui abbiamo semplicemente moltiplicato e diviso per E elevato a IQ R', ok? Quindi non è cambiato niente. And now we make explicit now the charge density as the total charge times the spatial distribution of the charge as a function of R prime. In the cube R prime, the cube R. Quando ci siete tutti, cambio pagina.
Io ci sono.
Anzi, fatemi continuare qua, c'è ancora un po' di spazio in basso. No, cambio pagina, dai, mi serve un po' più di spazio. Ci siete tutti?
Sì, io ci sono.
Ok. Va bene, dimmi tu allora. Ok, perfetto. Allora, andiamo adesso alla pagina 5. Ok, adesso facciamo un cambio di variabile, quindi definiamo la R grande come R piccolo meno R primo piccolo. Ok? So, change of variable. And so our integral now becomes still a double integral, e to the I q scalar capital R. Then we have q divided by 4 pi R modulus. Then we have our spatial distribution function, e to I q scalar R prime. And now we are in d R cube, d cube R, d cube small r, no, R prime. Questo non c'è. Okay. Allora, so far this is let's say an exact result in the Born approximation, of course. Now let's make an assumption. Okay. So in the case of elastic electron-proton scattering, that is a low energy process essentially, the transfer for momentum q is relatively small. And so essentially the electron probes the proton from a large distance. The resolution is low because the energy is low, and so the electron is far away from the proton. Okay, so essentially the electron probes the proton from a distance which is much larger than the proton size itself. And this corresponds to the limit where R is much, much greater than R prime. Okay. And so in this limit, we can now decouple the two integrals. And so this will become essentially e to the I q scalar R, q divided by 4 pi R in the cube R times the other integral. So we are factorizing the two integrals in this limit, in this approximation, e to the I q scalar R prime in the cube R prime. And so what we have here, so the first integral is essentially the matrix element for a scattering from a point-like object of charge q. So point-like object of charge q. So this is what we would have obtained in case of a point-like charge distribution. In our case, we are starting with a spherical distribution, so okay, with some spatial distribution. And so the second integral now accounts for the spatial distribution of the charge. And this was second integral we just call f q square, f of q, sorry, vector. So overall, what we obtain is that our matrix element, okay, for the scattering of an electron from a potential generated by a charge, spherical charge distribution, is given by the matrix element for a point-like object times a correction, okay, which accounts for the spatial distribution of the charge, which is called the form factor of the proton. Okay, we are not talking about proton at the moment, but in general of a charge distribution. Ok? È chiaro tutto il ragionamento?
Sì, certo.
Ok, adesso chiaramente applicheremo questo concetto al protone, chiaramente, assumendolo come una distribuzione sferica, a simmetria sferica di carica elettrica e anche di momento magnetico. Allora, torniamo adesso sulla slide. So this is our result, okay? And so the form factors, as you see, is nothing else than the Fourier transform of the spatial distribution of the electric charge. So the exact form of the form factor depends clearly on the charge distribution, okay, on how the charge is distributed in space. And under some simplifying condition, that is negligible recoil, plane wave approximation, in fact, the form factor is given by the Fourier transform of the charge spatial distribution. Now, of course, what we are interested in is to know how the charge is distributed inside the proton. So we want to extract this guy here from this Fourier transform, okay? And this mathematically we can do easily. We can just take the inverse Fourier transform, okay? So in principle, the charge spatial distribution, which is our goal, our final goal, can be obtained from the inverse Fourier transform, okay? So now you put a minus sign here, by using the Q-square dependence of the measured form factor. So suppose that you are able experimentally to measure the form factor, then you take this inverse Fourier transform and you obtain what you want to know. So how the charge is distributed in the proton, okay? However, in practice, this is not very accurate because the form factors can be measured only over a limited Q-square range. And this is due primarily to the fact that the elastic cross-section drops quite fast with Q-square. So at large Q-square, the elastic cross-section is essentially 0, but here you want to integrate from 0 to infinity, okay? So the Q dependence of the form factor are available experimentally only in a limited range of Q. Okay, so this integration will not be complete, and so the answer will not be precise enough. So the approach is essentially different. The common approach is instead to find a reasonable parameterization of the form factors, and then in terms of parameters, and then to fix the free parameters through a best fit of the data, so of the Q-square dependence of the measured form factors. So you measure the form factor as a function of Q-square, you make a best fit, you fix the parameters of your distribution, you put the distribution here, you solve the integral, you obtain your charge distribution. This is the logic. Now, in all practical cases, the charge density is assumed to have a spherical symmetry, okay? There is no reason not to assume this for a proton, for instance. And as a consequence, the form factor depends only on the scalar quantity Q-square. So we will not talk anymore about f of Q vector, but just of f of Q square, okay? Just because we are assuming a spherical symmetry. So there is not a preferred direction. So now the form factor can be calculated analytically for certain charge distribution described by simple radial function. So suppose your charge distribution is a point-like, so it is described by a Dirac delta. Then you take the inverse Fourier transform, and you would obtain a constant. So if you Fourier transform a point-like distribution, you obtain a flat form factor, a constant. If instead you want to be more, you want to put something more physical, so you put, for instance, an exponential charge distribution, you do the inverse Fourier transform, you obtain a so-called dipole distribution, okay? So there is a certain charge distribution which is now with some smoothness at the end, okay? So it mildly goes to 0, not sharply, but mildly. If instead you use a Gaussian charge distribution, you take the inverse Fourier transform, you obtain another Gaussian, okay, with different width. And then you can do something more sophisticated. For instance, you can assume, for instance, a uniform sphere or a Fermi function. Okay, there is a constant part and then with some drop, some smooth drop, and then you would like this so kind of the oscillating form factor as a function of Q square. Okay. So all the thing is making a good guess of the charge distribution, fix the parameters by fitting the experimental data, and calculate the inverse Fourier transform. And this will give you the shape of your charge distribution. Now, vediamo che ore sono un attimo. Ok. Ok, facciamo questa cosa qui e poi facciamo una pausa dopo, dai. So, if the transfer momentum Q is small enough, one can perform a power expansion of this exponential quantity here and derive the expression of the proton mean square radius. So let's do this. Allora, siamo alla pagina 6. Ok. No, c'era una cosa che non ho detto prima. Ah, non l'ho detta prima, sì, vabbè. Ok. So, we start from our form factor, f of q square, defined as the Fourier transform of the special charge distribution. So, we make explicit the scalar product. So this is f of r prime e to I q r prime cos theta in the cube. This is a cube, r prime. And now, if our transferred momentum q is small enough, we can take an expansion of this exponential. Okay, so this can be expanded as f r prime as the sum for n that goes from 0 to infinity of 1 over n factorial I q r prime cos theta to the n power in the cube r prime. And so now this we can write, we can develop the volume integration in polar coordinates. So this is going to be integral from 0 to infinity, integral from -1 to +1, integral from 0 to 2 pi. And then we have f r prime. Here we take only the first few terms of this power expansion. So the first one will be 1 when n is equal to 0. Then when n is equal to 1, we're going to have I q r prime cos theta, the first order term. Then we can go further. We get the second order term of expansion, q r prime squared cosine square theta plus additional terms, infinite in principle, in the phi, the cos theta, r prime square, the r prime. So now we have to split these integrals, okay, each per each order of the expansion. So for the 0 order, we have 4 pi from the angular integrals, and then we just left with the integral on r prime, f r prime square, the r prime. So this is integrating the first, the 0 order of this expansion, so the 1. Now we integrate the first one, so it's 2 pi q I. Here we have both the integral on space and the integral of theta, so it's 0 infinite, and inside we have the integral -1 1 of cos theta in the cos theta, and then we have the remaining terms, f r prime to the cube, the r prime, and then we have the second order term that is minus 1/2 q square 2 pi integral from 0 to infinity Also here we have to integrate over the theta angle. So this is a cos theta squared in the cos theta. And then we have f r prime. Now we have r prime to the 4th power in the r prime plus infinite terms, higher order terms.
Ok.
Ci siete? Allora, il coseno è una funzione pari, quindi il primo integrale fa 0, quindi questo va a 0. L'integrale invece sul coseno quadro è un integrale noto, fa 2/3. Quindi cosa c'è rimasto? 4π integral 0 to infinity f r prime squared di r prime for the 0 order. Then the first order goes to 0 and we jump directly to the second order, which is minus 1/6 4π q square integral 0 to infinity f r prime to the 4th power di r prime plus higher orders. Okay. Now we remember that the first term here is exactly 1, because this is nothing else than the normalization condition that we imposed before, if you remember. The one that allows the integral of the charge density to be exactly equal to the total charge Q, right? So this is just 1 minus 1/6 Q squared, and then we define this quantity, average R squared, that we will see in the next page. Ok, quindi quando ci siete ditemi, così vi do la definizione di R quadro nella prossima pagina.
Ci sono.
Anche.
Siete tutti? Ok. Allora cambio pagina. Andiamo alla pagina 7. Allora, R squared is the proton mean square charge radius. So defined as 4π integral 0 to infinity of r prime squared f r prime, and then we have the integration variable, which is r prime square in the r prime. Okay, and this is equivalent essentially, once one account for the normalization, as the ratio between the integral and the volume of the charge density r squared in the cube r, so the second moment, okay, of the charge density divided by the normalization condition, which is charge density into the volume. All these we call the proton mean square charge radius. Ok? Se volete è il valore d'aspettazione del quadrato del raggio della distribuzione di carica del protone. Ok? Allora, so what we obtain? We obtain that fq squared is equal to 1 minus 1/6 q square of this squared charge radius, okay? And so we can now take the derivative, the fq square with respect to q square, okay? And it's going to be minus 1/6 of r square, okay? Plus, again, okay, we are forgetting now the additional terms. Also here we have plus additional terms. So higher orders of q square, okay? These are higher orders of Q square. Okay? And so now we can invert this last relation to obtain R squared as minus 6, the derivative of the Q square divided by the Q square, the derivative with respect to Q square, okay? And if we want now to drop all the higher order terms, we calculate this derivative when Q square goes to 0. Okay, if Q square is 0, all the higher order terms will cancel automatically. Okay, and so we get here a very simple formula for the charge radius distribution of the proton. So with this condition, all the higher order cancel at every order, because they depend explicitly on Q square. Okay. Ok.
Quindi questa
Facciamo una... Sì, dimmi.
proprio la distribuzione di carica elettrica all'interno del, diciamo, del raggio del protone.
Sì, è il raggio al quadrato in realtà, poi prenderemo la radice quadrata di questo oggetto, ci darà appunto il valore d'aspettazione del raggio della carica elettrica del protone, della distribuzione di carica elettrica del protone. Sì.
Ok.
Quindi si ottiene derivando il fattore di forma rispetto a Q quadro nel limite in cui Q quadro va a 0. E poi prendendo la radice quadrata, ovviamente. Lo faremo tra un po', cioè andremo avanti tra un po', facciamo una pausa adesso di qualche minuto, sono 17, facciamo dai 5 minuti, facciamo 22, c'è ancora un po' di roba da oggi in questa lezione. Ricominciamo a 22. Ok, riprendiamo. Ci siete tutti?
Io ci sono.
Ok, allora, rivediamo un attimino sulla slide quello che abbiamo ricavato. Ok, quindi diciamo questo valore atteso del raggio quadratico medio del protone l'abbiamo visto, diciamo, definito in questo modo qui, ok? E dal punto di vista, diciamo, sperimentale, se noi conosciamo l'andamento in Q quadro del fattore di forma, ne deriviamo la forma funzionale, la calcoliamo la derivata Q quadro uguale a 0, moltiplichiamo per meno 6 e otteniamo esattamente questo qua. Dal punto di vista invece del calcolo, ok, se noi invece conosciamo la distribuzione di carica dell'oggetto che stiamo considerando, un protone, una particella, quello che volete, allora ci basta applicare, diciamo, questa definizione qui, che è la ridefinizione, se volete, diciamo, matematica del secondo momento, quindi, ok, in termini della distribuzione spaziale. Ed è quello che faremo adesso in un esercizio. So calculate the RMS radius for a particle with a mass 0.84 GeV squared, c squared, and with this kind of charge distribution, so with an exponential behavior. Allora andiamo di là. Quindi questa è la pagina 8 e questo è problem 7.1. Okay, so according to the test, the charge distribution is of the form rho 0. Oh, sorry, let me go back once more. Okay. E to the minus mc divided by h bar r. Okay. So it goes, it decreases exponentially with the distance from the center. Okay, so we use now the definition of r squared as the charge distribution times s squared in d cube r, where the charge distribution must be properly normalized, so we have to divide by this volume integral. We substitute here the charge distribution, so we have a rho 0 e to the minus mc over h bar r times r squared in the cube r, divided by the normalization integral, so rho 0 e to the minus mc over h bar, simply in the volume. We translate this into polar spherical coordinates, so this integral 0 to pi in the phi, 0, integral from 0 to pi of sin theta d theta, integral from 0 to infinity of the charge density, so 0 e to the minus mc over h bar r. And now we have, where are we? Yeah, now we have a fourth power of r, because now this is the special integral in the r. And in the denominator, we have, in analogy, integral 0 to pi in the phi, integral 0 to pi sin theta d theta, integral 0 to infinity of rho 0 e to the minus mc over h bar r, simply in r squared dr. So clearly here we can simplify a lot of things, okay? So this integral is the same, this integral is the same, and also the rho 0 is a constant that we can drop here. So overall, we are left with the spatial integrals, integral from 0 to infinity of e to the minus mc over h bar r, r to the fourth power in the r, and integral from 0 to infinity e to the minus mc h bar r, r squared in the r. So now we have to solve these two integrals. These two integrals are known integrals, and they are of the type, in general, e to the minus alpha r, r to the n in the r, and the solution is of the type n factorial divided by alpha n plus 1. Okay, so in our case we have n equal 4 in the numerator, okay, and we have n equal 2 in the denominator. So we can just take these known solutions. So we have for the numerator 4 factorial divided by the argument of the exponential, which is mc divided by h bar to the 4 plus 1 to the power 2. And then in the denominator we have 2 factorial divided by mc over h bar to 2 plus 1. Okay, so n factorial divided by 2 factorial is just 12. And then we have mc over h bar to the second. And this we can more conveniently write in terms of our beloved constant. So mc squared divided by h bar c, that we know is 200 Fermi per MeV. And so we can now easily substitute the values. And so we have 12 divided by the mass of this particle is 840 MeV. The constant h bar c we know is of the order of 200 MeV per Fermi. This is squared. And the result is 0.68 Fermi squared. Okay, so now we just want the root mean square radius. So r root mean square, which is just the square root of this. That is the square root of 0.68 Fermi square. This is 0.82 Fermi. Okay, so this particle with this mass and this charge distribution has a root mean square radius of 0.82 Fermi. Tutto chiaro?
Sì.
Ok. Torniamo adesso sulla slide. Ci siete tutti? Avete copiato tutto?
Sì, io ci sono.
Benissimo. Allora, torniamo qua. E adesso completiamo il nostro viaggio su questa evoluzione della sezione d'urto man mano che cresce l'energia e man mano che riduciamo di volta in volta le approssimazioni che abbiamo fatto all'inizio, partendo da quella più approssimata possibile, che era quella di Rutherford. Okay? So now the last step is to take into account the finite size of the proton in terms of the form factors. Okay. So if you now indicate capital Q squared, the form momentum transfer, okay, we end up, so our cross section, this was the last version, okay, with the anomalous magnetic moment. When we now take into account also the finite size, so we introduce also the form factors, the cross section becomes like this. So the functional form is essentially the same, okay? We have still a constant times this tangent square, etc. But now the form factors of the proton or the neutron enter into the game. And in particular, there are two types of form factor, F1 and F2, which are known respectively as the Dirac form factor and the Pauli form factor, okay? So this is now the most general expression for the cross-section when you account also for the finite distribution or finite size of the proton, and so of the charge distribution. But this we can express in a more convenient way. Okay, so the electron proton elastic scattering cross section is more conveniently expressed in terms of suitable combination of these Dirac and Pauli form factors, okay, which are called the electric and magnetic form factors. So the electric form factor for either the proton or the neutron is given by this combination of the Pauli and Dirac form factor and this anomalous magnetic moment, the mass, and the transfer Q square. And the magnetic form factor is given by this other combination of the two. Okay, so the electric describes the distribution of electric charge into the proton, and the magnetic form factor describes the distribution of the magnetic dipole moment, of the magnetic moment in the proton, essentially. Okay. Now, what is now the limit of this object when the q square goes to 0? Q square goes to 0, that means that we have essentially 0 spatial resolution. Okay, so again, we consider the proton in this limit as a point-like object. Okay, and so in this limit, they are normalized exactly to the electric charge of the proton or the neutron in terms of the electron charge. So 1 for the proton and 0 for the neutron, where q square goes to 0, you see here. And the magnetic form factor just reduced to the anomalous magnetic values, okay, for the proton and for the neutron. These are the way they are normalized in the limit where q square goes to 0. So now we can rewrite our cross-section, substituting, this combination of F1, F2 in terms of GE and GM. And this is now how it looks like. This is called the Rosenbluth formula, okay? So it is the Mott cross-section for finite mass, and with all this term that takes into account of everything we discussed so far. So, okay, so also including the electric and magnetic distribution of the proton. Now, let's consider two limit behavior. So at low q square, here we define the tau in this way. So q square divided by 4 times the squared mass of the proton. So at low q square, times becomes a smaller, a number much smaller than 1. So suppose that q square goes down much below the mass of the proton, okay? So if tau becomes such a small quantity, we can completely neglect all these terms which are multiplied by tau, okay? And essentially, the cross-section only depends on the electric form factor GE. So this is the only surviving term here in this limit, okay? On the other hand, if now q square is very high, so now tau is much, much greater than 1, that means that the q square is much greater than the mass of the proton, then all the terms with tau dominates, so we can now neglect the electric form factor, and essentially only the magnetic form factor dominates in the cross-section. So the cross-section will reduce to this simple form here. Clearly, in between, we have both contributions. So let's now summarize what we have learned from the beginning of our journey. So we started with the Rutherford cross-section, that is a scattering of a point-like spinless electron on a point-like infinite mass nucleus, okay, spinless, and this is the Rutherford cross-section. Then we allow the electron to be relativistic and to have spin, and so now we jump to the Mott cross-section, okay, which is the Rutherford with this cosquare correction term that suppress the backscattering case. Then we allowed also for the recoil energy of the proton, okay, so we had to make an additional kinematic term for this. Then we allowed also for the proton spin. So now the proton is a point-like particle with spin 1/2, so it is a Dirac particle, okay? And this is what we obtained here. And finally, okay, in between we also put there the anomalous magnetic moment, clearly. And then at the end, we also include now the spatial distribution of the electric charge and magnetic momentum of the moment of the proton, and so we end up at the end with the Rosenbluth formula, essentially, okay, in terms of GE and GM. So from top to down, we increased the energy and we released one by one our initial approximations. Okay. Now, let's now see how we can infer or measure GE and GM experimentally. Okay, so experimentally, the q square dependence of the electric and magnetic form factor of the proton can be inferred from elastic electron-proton scattering, okay, by changing the electron beam energy. Okay, and this is the way. So this is the procedure. So the differential cross-section is measured at a specific angle. So you see here how many, 45, 60 degrees, 75, 120, 135. So you fix your spectrometer at a specific angle, and you measure the cross-section for different beam energies. Okay, and this corresponds to measuring the cross-section for different q square, because the q square is kinematically related to the beam energy by this relation here. Okay, so you change the energy, and as a consequence, you change the q square. You fix your angle, and so you measure your cross-section at a fixed angle, but at different values of q square, essentially. Okay, this is the first step. Second step you evaluate the cross-section now at a fixed q-square, but over a range of scattering angles. So you fix your q-square, for instance, 0.992, and you calculate the cross-section now as a function of the angle. Okay, so the angular distribution of the cross-section. You do this here, you change value, take this here, you change again value, take this here, etc. And now you can plot all these numbers as a function of the angle. So in particular, the square tangent of the angle. Okay. So this is just the example of this fixed value of the q-square. So you fix the q-square, and you take all these values, and you report all these values as a function of the angle, essentially. So the tangent square. Okay. Now, let's have a look again on the Rosenbluth formula. Okay, if we divide the Rosenbluth formula by the Mott term, we end up just with this term here, the one that includes the electric and magnetic form factor, as we've seen before. Okay, and this we can easily parameterize as with a linear function. Okay, so a plus b something. Okay, so if we plot, so if tangent square is our variable, this is just the equation of a line. Okay, a linear function. So the first parameter, A, accounts for all these guys here, and the second parameter, which is la pendenza della retta, insomma, okay, il coefficiente angolare, is given by this other term here, okay? And this relation allows to extract simultaneously the electric and magnetic form factor at a given value of q-square, so still we are fixing q-square to a single value, just by doing a linear fit of this data here, okay? So you do the fit, you extract the two parameters. The first parameter is given by this combination of G and GM, and the second parameter gives you GM. Okay, so you know B, you also know GM, you substitute here, you also get G. You know everything. And this technique is called the Rosenbluth separation. Okay. Now, clearly, this is only for some specific value of q-square. Then you have to repeat this procedure for all the other possible values of q-square. So repeating this measurement at different values of q-square. So back here to the plot before. So now you start from a different value of q-square and you do the same procedure. Then you change again, you do the same procedure, etc. At the end, you would obtain now the q-square dependence of both your electric and magnetic form factors. Okay? And this you can now report now in a plot. So you now report your form factor as a function of q-square. And you get separately, of course, the distribution of the electric form factor and the magnetic form factor. Okay, once we've done all this procedure. So what we can learn now from this distribution here. First of all, it turns out that the measured form factor decrease with increasing q-square. Okay, so they are very high at small q-square, and then they go essentially to 0 at large q-square. And this is essentially what we also expected, because this provides an experimental demonstration that the proton has a finite size, in the sense that as the q-square increases, so as long as we move in this direction, also the spatial resolution increases, and therefore the electron, which is our probe, sees a smaller and a smaller fraction of the total proton charge, because the resolution is increasing, okay? And so your form factor goes down this way. And then when the energy is very high, so the q-square is very high, then the form factor essentially vanishes, because now essentially the total cross-section only is mainly given by the inelastic cross-section. So the elastic cross-section that you need to measure form factor essentially goes to 0 at very high q-square. This is why essentially they go to 0 at high q-square. Now, if you now compare these two, okay, you find that the dependence of GM and GE are essentially the same, the q-square dependence, apart from a scale factor. And this shows essentially that the charge distribution and the magnetic moment distribution within the proton are consistent. And this is encoded in the so-called scale law. Okay, so first of all, if you now go back to q-square goes to 0, okay, for the two, you realize that the electric form factor at q-square goes to 0 give you exactly 1, that is the electron charge, okay, as we was imposing before. And if you extrapolate your magnetic moment, magnetic form factor at 0, you end up exactly to 2.79, which is the anomalous magnetic moment of the proton, okay? And the two, in fact, are just related by this simple scale relation. So the electric form factor is just exactly the same, or more or less the same, of the magnetic form factor just by a scale factor, which is the inverse of the either proton or neutron magnetic moment, the anomalous magnetic moment. Okay. And what the electric form factor of the neutron is 0, because the neutron is from the external part clearly a neutral particle. Okay. Now, in the low Q-square region, the experimental data are reasonably well parameterized by an empirical function, which is called the dipole function, okay, which also incorporates the scale law. So this is the way. The magnetic form factor is essentially the same as the same Q-square distribution as the electric form factor, apart from a scale factor, which is the magnetic moment. So this is 2.79 for the proton, and then we have this dipole dependence of Q-square, which is essentially this functional form here that you see drawn here, this line here. So this is a typical dipole behavior. Okay. What now if we take the inverse Fourier transform of our form factor, okay, with this dipole shape? So by taking the inverse Fourier transform of the dipole function for G at log square, one obtain what we expect the charge distribution. Okay, so this is the process at the in the opposite way. And it turns out that if your electric form factor is well parameterized by a dipole law, okay, you obtain for your charge distribution an exponential decay law, just the one we used in our exercise before. Okay, in particular here these parameters rho 0 and a are fixed in a fit to experimental data. Okay, so the inverse Fourier transform of a dipole function, which is this way, gives you an exponential charge distribution. And this is fine. It is not a sharp distribution. Okay, it is a mild decrease. Okay, and this is justified by the fact that the protons and neutrons are neither a point-like nor homogeneous charge spheres, but are rather quite a diffuse system, of course, with a spherical symmetry. Okay, so the charge distribution does not drop abruptly, but very smoothly. Okay. Now let's do this here, this exercise. Show that the electric form factor of a charged particle, which this charge of distribution, so exponential, is indeed of the dipole form. Allora andiamo qui. Ok. Allora aspetta, prima di andare avanti, ci siete fin qui? Avete capito questa questione del dipolo? Okay, è una formula empirica che rappresenta molto bene i dati da quella forma funzionale lì. Adesso facciamo l'esercizio inverso in cui noi sappiamo che la distribuzione di carica è esponenziale, ci aspettiamo quindi che il fattore di forma abbia un andamento di tipo dipolo. Ok, allora questo è pagina 9, problem 7.2. Okay, so from the text we learn that our charge distribution is an exponential one, e to the minus mr, okay? And so we calculate now the inverse Fourier transform. So we try to derive the shape of the form factor given now this charge density, rho 0, e to the minus mr, and then we have the inverse Fourier transform, so plus I q r in the cube r. Okay, we can put rho 0 outside, it is a constant. And then here we have e to the minus mr times e to the I q r cos theta in the cube r. And as usual, we develop the volume integral in polar coordinates. So this is rho 0, integral 0 to 2 pi the phi, integral 0 to pi sine theta the theta, integral 0 to infinity e to the minus mr e to the I q r cos theta r square dr. So there is no dependence on phi, so this gives us immediately a 2 pi from the first integral. So we have a 2 pi rho 0 And the second we can write in terms of the cosine. So this is equivalent to integral from -1 to 1 of the cos theta. And then this we can simply copy. Yes, e to the minus mr, e to the I q r cos theta r squared dr. Now we take the integration over theta. So this is 2 pi rho 0 integral from 0 to infinity of e to the minus mr, and inside we solve the integral on theta. E to the I q r cos theta in the cos theta, and then we are left with r squared dr. So the integral in theta is trivial, it's just an exponential. So this is 2 pi rho 0 integral from 0 to infinity e to the minus mr. And then we have 1 divided by I q r, and then we calculate the result on the two estremi di integrazione, e to I q r minus e to minus I q r squared dr. And so this we can even write as 2 pi rho 0. We put outside I q, and then we are left with the integral on the space coordinates e to I q r minus e to minus I q r e to the minus mr r dr, where we simplify this with this. And this we can split into integrals. So this is 2 pi rho 0 on IQ. And then we have the integral from 0 to infinity of e to the minus IQ plus m r dr minus the other integral 0 to infinity e to the minus IQ plus m r in r dr. Now let me call this integral A, and you can already realize that both integrals are of the shape of the one that we used in the previous exercise. So they are of the type 0 infinity e to the minus alpha r dr, okay, which is 1 over alpha squared. Okay, in general, this is of the type integral from 0 to infinity of e to the minus alpha r to the n in the r, and this gives up n factorial divided by alpha to the n plus 1. In our case, we have n equal 1. Ok? Quindi sono due integrali noti, essendo n uguale 1, semplicemente danno 1 su alfa quadro, dove alfa è l'argomento dell'esponenziale. Quindi andiamo adesso a sostituire. Ci siete tutti in questa pagina?
Sì.
Io ci sono.
Ok, allora andiamo alla pagina 10. Allora, quindi, as a consequence, integral A is 1 divided by alpha squared, so m minus IQ squared. And integral B is 1 divided by m plus IQ squared. So let's now substitute everything inside. So our form factor is 2 pi rho 0 divided by IQ. And so we have 1 divided by m minus IQ squared minus 1 divided by m plus iq squared. Let's make some very trivial algebra. 2 pi rho 0 divided by iq, minimo comune multiplo, m plus iq squared minus m minus iq squared divided by the product squared. So this is m minus iq times m plus iq all squared. Adesso sono proprio passaggetti di algebra elementare. Quindi abbiamo m quadro più 2iqm meno q quadro meno m quadro più 2iqm più q quadro diviso m quadro più q quadro al quadrato. Qui possiamo semplificare un po' di roba e otteniamo 2π greco rho 0 diviso iq per, andiamo a sommare, ci rimane 4iqm diviso m quadro più q quadro al quadrato e semplifichiamo iq, per cui alla fine abbiamo 8π greco m rho 0 diviso m quadro più q quadro al quadrato, ovvero 8π greco m rho 0, tiriamo fuori la massa alla quarta, 1 più q quadro diviso m quadro al quadrato, ovvero 8π greco rho 0, dunque su m al cubo, sì, abbiamo una massa anche sopra, quindi questo diventa m al cubo, per 1 diviso 1 più q quadro su m quadro al quadrato, ovvero proporzionale a 1 più q quadro su quadro alla meno 2, che è proprio la funzione di dipolo. Ok? Quindi assumendo la distribuzione di carica abbiamo calcolato la trasformata di Fourier inversa e abbiamo ricavato la forma, la dipendenza da q quadro del fattore di forma.
Ok.
Allora, abbiamo 5 minuti, vediamo se riusciamo a finire a completare la lezione, ancora qualche slide da mostrarvi. Allora, quelli che vedete qui sono delle word data, okay? Sono risultati di tanti esperimenti messi tutti insieme, in cui vedete sostanzialmente il rapporto tra il momento, il fattore di forma elettrico diviso, diviso la forma di dipolo, la forma funzionale, che quindi il rapporto infatti è molto vicino a 1, come vedete, e un rapporto un po' meno favorevole, un po' meno uguale a 1 per quanto riguarda invece il fattore di forma magnetico corretto per il momento magnetico, ok? Questo vuol dire che la forma di dipolo funziona meglio per quanto riguarda il fattore di forma elettrico e un po' meno per quanto riguarda quello magnetico. So measurement of GM at high Q square, okay, so when we now move to high Q square, show sizable deviations from the dipole distribution, order of 30%, so you drop from 1 down to 0.70, okay, so order of 30% when the Q square is as high as 30 GV squared. And they also show some slight deviation also in the lower Q square region, so when Q square is smaller than 10 GV squared, okay? Whereas for the electric form factor, the agreement is pretty much good. Now, what about now the mean square radio discussed before? So the mean square radio of the charge distribution in the proton and of the magnetic moment distribution in the proton and in the neutron are approximately the same, okay? And we can calculate using the formula that we derived before, okay? So as a first approximation here, instead of the measured form factor, we can put the dipole analytical form here. So we take the derivative, we put Q squared to 0, we multiply by 1/6, and we obtain this value here. So when you take the square root, you obtain that the expectation value of the root mean square radius of the proton is 0.81 Fermi. However, since we've seen that the agreement with the dipole form is not always perfect, okay, a better approach is instead to use data. So not using the form, the mathematical form of the dipole, but instead using the experimental data and to extrapolate the data down to q squared goes to 0, okay? And once you do so, okay, and you fit this with, of course, with a proper form, you can now substitute this into this formula here, and you obtain at the end as a root mean square of the proton 0.88, essentially 879, which is now the best value for the charge of the proton. Okay. What about now the charge of the pions or the kaons, for instance? Okay. Okay, now from the experimental point of view, it is more complicated because clearly you cannot have a target of pions or target of kaons to perform your elastic scattering, okay? And so you need a different technique. In particular, the method that has been used is the following. It consists of producing high energy beams of pions or kaons, and this you can do. You can provide beams, but not target, clearly. And to scatter those beams on the atomic electrons, okay, of some target. So essentially, you do the opposite thing. Okay, you now fix the electron and you use a beam of pions or kaons. And then at the end, you analyze the angular distribution of the ejected electron, so the one here in the final state. Clearly, pions and kaons are pseudo-scalar mesons, as you know, so they come with spin 0, and as a consequence, they have no magnetic form factor. They only have the electric form factor. And it turns out that the best fit of the pions and kaons form factor is obtained by this monopole distribution, okay? So the q-square dependence is different than the one in the proton. It is now a monopole, not a dipole. And these are now the experimental data compared with this monopole distribution. And then once you extrapolate the distribution down to q-square equals 0, you can calculate your root mean square radius. And for the pion, it turns out to be 0.67 Fermi, and for the kaon, 0.58 Fermi. Now, the last couple of slides. So, all this is obtained through the Rosenbluth formula and the Rosenbluth separation technique that we discussed before. Now, more recently, starting from essentially in the last 20 years already, the electric and magnetic form factors have been determined at the Thomas Jefferson Lab in the US with a different approach, which is the recoil polarization method. And the idea is the following. So suppose now you have a polarized electron beam. So electrons with the spin aligned parallel or anti-parallel to the beam direction, okay? When you scatter a polarized electron beam on an unpolarized proton, at the end, in the final state, the proton becomes polarized. So there is essentially a polarization transfer from the electron beam to the target proton, okay? And in particular, in general, the proton acquires two polarization components, a transverse component, PT, and a longitudinal component, where transverse and longitudinal are, of course, with respect to the direction of the beam, okay? Or to the proton momentum in this case. Why is this useful? Because now you can very simply calculate the ratio between GE and GM by knowing these two components, so the polarization component of the proton, the transverse and the longitudinal, okay? And then by knowing, of course, the energy of the initial and final electron and the mass of the proton, and by measuring the angle. So these are all experimental quantities that you have to measure carefully, but once you do so, you immediately obtain the ratio between the two, okay? And this is now the surprise, okay? The surprise is the following. When you now plot the electric or magnetic form factor, actually the ratio of the two, as a function of q-square, you don't obtain anymore something consistent with 1, as you would expect from the Rosenbluth separation and from the scale law that we showed before, but you see that the ratio drops quite fast. Okay, as soon as q-square goes increases, the ratio goes as down as essentially 0. So there is a huge discrepancy between the Rosenbluth result and these new results based on the polarization technique. So rather than being constant, the ratio of GE over GM, corrected by the magnetic moment, decreases linearly. This is linearly with q-square down approximately to 10% at HGV. And this can be interpreted by saying that actually the electric charge distribution and the magnetic charge distribution are different. And in particular, the electric charge distribution extends to larger radii than the magnetic moment distribution. Okay, this is the interpretation of this ratio being not 1. So how can we now reconcile the two? Okay, so either this is wrong or this is wrong, clearly. Now, this was okay, there was a lot of theory work trying to understand this discrepancy. And now the favorite explanation is that for this discrepancy is that one has also to consider not only exchange of single photon, that is the zero order process, but also higher order process where two virtual photons are exchanged in the elastic scattering between the electron and the proton. Okay, and it turns out that this two-photon correction is substantial for the Rosenbluth separation method, while it only hardly affected the double polarization measurement. Okay, so if essentially what people is now working on is try to correct the Rosenbluth data with this two-photon contribution and try to see if this data can be reconciled with the polarization method, which is not essentially affected by this correction term. Okay. Let me conclude now with the neutron. Okay, so the neutron from the externally appears, of course, a neutral object, okay, from outside, but clearly inside it contains quarks, and quarks are charged particles, okay? So they of course contribute to the charge and also clearly to the magnetic moment of the neutron, okay? Now, the experimental study of the neutron form factor is complicated by the fact that it is not possible to use pure neutron target, okay? There's no way to create a pure neutron target. What you can do, for instance, is to create a deuteron target, but then you have to correct, okay, for the effect of the proton and neutron binding energy in the deuteron. So you can make measurement on the deuteron, but then you have to correct for the proton contribution. However, precise results are obtained now from this double polarization method or recoil polarization method. And you see here now the first measurement of the electric form factor from the neutron, okay, which is indeed very small, but it is not zero. So the data are consistent with this kind of shape. So it starts from 0, then it increases, and then it slows, it decreases as q square increases. Okay, so the results show that the electric form factor of the neutron is not 0, but it rises from 0 up to 0.06 and then around 0.3 GeV squared, and then it goes down slowly. Ok, questo è tutto. Domande, dubbi, curiosità?
No, io sono a posto,
Ok.
grazie.
Ah no, una piccola
Vabbè,
domanda su cose un po' più vecchie, nel senso quello che abbiamo fatto un po' di tempo fa nella lezione. Quando abbiamo chiamato Q grande il momento scambiato, perché il valore di Q piccolo era negativo, ha un senso fisico questa cosa? Nel senso, perché otteniamo un Q quadro minore di 0 a partire da uno scambio di momento?
Bah, non è che cioè, non ti so rispondere al volo su questa cosa. Diciamo, sì, l'algebra dei quadri momenti ti dà quel valore negativo, c'è poco da fare, te lo prendi.
Sì, sì.
La questione, oddio, non vorrei dire una sciocchezza adesso. Prendilo per buono. Nel senso, se fai il calcolo ti viene negativo, c'è poco da fare. Il problema è lavorare con quantità negative, sembra un problema, per cui si ridefinisce positivo col Q quadro grande.
Ok, ma non ha attualmente un'implicazione di qualche tipo. Ok.
Adesso su due piedi non ti so rispondere, dovrei pensarci un attimo.
Nessun problema.
Ok.
Grazie.
Va bene, allora con la lezione di oggi abbiamo completato la parte dello scattering elastico elettrone-protone, quindi abbiamo visto insomma tutte quante queste approssimazioni che abbiamo rimosso man mano fino ad avere una visione in cui si tiene conto di tutto, quindi della carica, dello spin, delle dimensioni finite, eccetera. Da domani invece andremo sulla parte inelastica, quindi aumenteremo l'energia e vedremo che succede quando lo scattering elettrone-protone diventa inelastico o addirittura profondamente inelastico. Va bene, direi di chiudere, stiamo già sforando parecchio la lezione di Pagliara, quindi ci salutiamo, ci vediamo domani alle 11.
Va bene, buona giornata.
Ok, buona giornata, interrompo la registrazione.
Arrivederci.
Arrivederci.
Arrivederci.